Hello there, Mr. Sutton here, bringing you the BC Calculus 7-8 Extra Practice Number 2 solutions on interval of convergence. On this problem, I'm trying to find the radius of convergence for this series, so we'll start by using the ratio test. So I have my n plus 1th term over the nth term. That's going to be n plus 1 times x to the n plus 1 over n plus 1 plus 2, so n plus 3. And then that's all going to be over just the nth term. There's just this formula down here. Same change flip, we've got n plus 1 and x to the n plus 1 times n plus 2 in the numerator. Down below we have the n plus 3 and the n x to the n. The only thing we can really reduce at this point is these x's. Using our exponent rules and subtracting, we just have an x upstairs and the x downstairs is gone. So upstairs then we have n plus 1, we have an x, we have an n plus 2. And then down below we have an n and an n plus 3. Now as n approaches infinity, the plus 1, plus 2, and plus 3 can be ignored. Those are smaller growing, lesser terms. So we essentially just have xn squared in the numerator and n squared in the denominator, which we can just reduce to x. So we have absolute value of x after we apply that infinite limit. And the nth ratio, the nth ratio of all of this stuff, for this thing to converge has to be less than 1. So we can write absolute value of x less than 1. And since this is in x minus a less than 1 form, since the coefficient on x is just 1, whatever value is over here is going to be the radius of convergence. So our radius of convergence then, our ROC, is just going to be 1. For this problem, we're trying to find the radius of convergence for this series. Now the key on this one is recognizing that we have a geometric series. We have all these things being raised to the nth power. The r value for this is just all of this stuff being raised to the nth power. So the negative out in front and also this 4x plus 1 business there. To find the radius of convergence for the geometric series, we just have to set the absolute value of r, which is just going to be 4x plus 1, less than 1. And then we have to put this in x plus a equals 1 form, essentially. So this is going to be here, let's see here, divide everything by 4. We have x plus 1/4 in absolute value, less than 1/4. And then that means that our radius of convergence is just going to be whatever number is out here, which is just 1/4. For this one, we're trying to find the radius of convergence for this series. Since this is not quite a geometric series, because we have this n out in front kind of messing stuff up, we're going to have to use the ratio test. So I'm going to have the limit as n approaches infinity of the absolute value of n plus 1th term over nth term. So we've got n plus 1 times x to the n plus 1 over 10 to the n plus 1. That whole thing up there is the n plus 1th term. And then we have to do the nth term down here, which is just the summand of this series. Now using a little same change flip, we've got n plus 1 times x to the n plus 1 times this 10 to the n. All of that over 10 to the n plus 1 times n and x to the n. All that we can really reduce here is these x's and these 10s. So let's see here. It looks like subtracting our exponents, we're still going to have an x left upstairs. And this x down here will be gone. And then with the 10s, we'll have a 10 down here. But this 10 up here will be completely canceled out. So we're going to end up with n plus 1 times x. And then that's going to be over, let's see, we still have an n and a 10, so 10n. Now as n approaches infinity, the plus 1 in this n plus 1 can be ignored. So we really just have xn over 10n. Canceling out those n's, we just have x over 10 in absolute value. And now the limit has been applied, so it's gone. So using our interval of convergence setup, this has to be this whole absolute value now has to be less than 1 for this series to converge by the ratio test. And to get the radius of convergence, we have to have this in 1x minus a form. So essentially the coefficient on x has to be 1. To make that happen, we just multiply everything by 10. So we get absolute value of x less than 10. And then now that we're in that 1x form, the radius of convergence is just whatever's on the right side of the inequality here, which is 10. For this problem, we want the interval of convergence. Since this is not a geometric series, we have to use the ratio test. So I have limit as n approaches infinity of the n plus 1th term over the nth term. So n plus 1th term, and by the way, that's all an absolute value. N plus 1th term, that's going to be n plus 1 times x to the n plus 1 over, I guess this would be n plus 3 in that case. I go n plus 1 plus 2, n plus 3, same difference. And we have all of this stuff that was originally here down in the denominator. So multiplying by the reciprocal, I have n plus 1 times x to the n plus 1 times n plus 2 in the numerator. And down below, we've got what was already in this denominator, so n plus 1 plus 2 or n plus 3. And we also have n and x to the n. So the x's here can cancel a little bit, leaving us with just an x upstairs, along with the n plus 2 and the n plus 1. And downstairs, we still have n plus 3 and n. So as n approaches infinity, the plus 2, the plus 1, and the plus 3 are all going to be gone. So we have xn squared over n squared, which is the n squareds are just going to reduce, giving us just x inside the absolute value. So we can write then absolute value of x is less than 1 to set up our interval of convergence, because ratio test, for this thing to converge, the ratio of the n plus 1th to the nth term has to be less than 1. So that means, just turning this into the double inequality here, negative 1 is going to be less than x is going to be less than 1. That's our kind of rough draft of our interval of convergence. To see if we're actually converging at the endpoints, if these are equals or not equals with these inequalities, we have to test each of those endpoints out. So let's test out negative 1 first. At x equals negative 1, this series can be written as negative 1 to the n times n over n plus 2. So testing this for convergence, we'll first use the nth term test, the limit of this expression as n approaches infinity. So we can ignore this 2 here. You've basically got a plus or minus because of this negative 1 to the n. And we have n over n, which reduces to 1. So this is plus or minus 1. Since that does not equal 0, since the nth term is not approaching 0, this diverges by the nth term test. So this less than here is just a less than. It's not going to be a less than or equals. Now we test out 1. If we plug 1 into the original series, now we just have, let's see, 1 to the n, which is just 1. So we have n over n plus 2. Using the nth term test on this one, so limit as n approaches infinity for this stuff, that's just going to be 1, which still is not 0. So this one also diverges by the nth term test, which means that our rough draft of our interval of convergence is actually going to be the final draft. We're going to have negative 1 less than x less than 1, and that's it. On this one, we're trying to find the interval of convergence of x to the n over n factorial. So since this is not a geometric series, we start with the ratio test. I have the limit as n approaches infinity of the absolute value of n plus 1th term, that's x to the n plus 1 over n plus 1 factorial, all of that over the nth term, which is just x to the n over n factorial. Now, multiplying by the reciprocal, I have x to the n plus 1 times n factorial in my numerator. And in the denominator, I have n plus 1 factorial times x to the n. It looks like we can reduce a few things. So the x's can reduce, subtracting my exponents. We're just going to end up with x to the first power in the numerator here. And these factorials also reduce. If we cancel out n factorial with n plus 1 factorial, well, remember, n plus 1 factorial is really just n plus 1 times n factorial. So when these factorials cancel, all that's left is an n plus 1 down here. So to summarize, we have an x left upstairs, and downstairs we just have n plus 1. Now, as n approaches infinity, the denominator is the only thing growing here. So this is a bottom-heavy function that just goes to 0. For this interval to converge, the ratio of these terms here, n plus 1 to the nth term, the ratio has to be less than 1. Since 0 is less than 1 no matter what you plug in for x, since this is always true, that means our interval of convergence is all x values. So negative infinity less than x less than positive infinity. To find the interval of convergence on this series, it helps to recognize that this is a geometric series. If we rewrite this a little bit here, we can write this as x minus 8 squared over 4, all of that raised to the nth power, just kind of undistributing this n from the numerator and denominator. So we see here that we have a geometric whose r value is x minus 8 squared over 4. So we can set the absolute value of r less than 1, and solving that will give us our interval of convergence. So to get to the bottom of this, let me start by multiplying both sides by 4. And then if I just square root over here, we have x minus 8 inside an absolute value still, less than 2. And we can't write plus or minus 2 because, well, the absolute value of something can't be less than a negative number. So now, getting rid of the absolute value, we can write negative 2 less than x minus 8 less than positive 2. And then just adding 8 everywhere, we've got 6 less than x less than 10. Now, since this was a geometric series where there is no ambiguity whatsoever at 1, it just has to be less than 1, we are guaranteed that this is the interval of convergence and don't need to test the endpoints. For the interval of convergence on this one, it helps to note that this is a geometric series, which we can see if we rewrite this as x minus 2 over 10, all of that raised to the nth power. So if we were to do that, we'd see that we had an r value here of x minus 2 over 10. That's what we keep multiplying by over and over again to get the next term of the series. So to find the interval of convergence, we just take the absolute value of this r and make that less than 1, and then just solve for x. So multiplying by 10, we've got x minus 2 absolute value less than 10. And then getting rid of the absolute value, we can write negative 10 less than x minus 2 less than positive 10. Adding 2 everywhere, we have negative 8 less than x less than 12. And since this was a geometric series, there's no ambiguity. We don't have to test the endpoints. This is the interval of convergence. To find the interval of convergence on this series, since this is not a geometric series, we're going to have to use the ratio test. So I'm going to take the limit as n approaches infinity of the absolute value of the n plus 1th term over the nth term. So for the n plus 1th term, we have n plus 1 factorial times x minus 3 to the n plus 1. And all of that is going to be divided by just the nth term, so n factorial over x minus 3 to the n. These factorials can cancel a bit. That'll leave us with just an n plus 1 upstairs. And the exponential terms also cancel, leaving us with just a single x minus 3 in the numerator. So when all is said and done, we just have limit as n approaches infinity of n plus 1 times x minus 3. Now as n grows to infinity, this whole term in here is going to grow to infinity. And since infinity is greater than 1, no matter what you plug in for this x value here, that means that the interval of convergence is just going to be the center here, x equals 3. Nothing else is going to make this thing converge, only the center. For this problem, we have a Taylor series about x equals 5, and we have the nth derivative of f at x equals 5 given by this formula here, and also f of 5 is 1/2. First task is to write a third-degree Taylor polynomial for f about x equals 5. There's a lot going on in this problem, so I'm going to start with kind of a general setup. So my polynomial, which I'm going to call P3, is going to equal f of 5 plus f prime of 5 times x minus 5 plus f double prime of 5 times x minus 5 squared over 2 factorial plus f triple prime of 5 times x minus 5 cubed over 3 factorial. So a lot to keep track of. Really, all I'm going to change on my next step is I'm actually going to apply this derivative formula to f prime, f double prime, and f triple prime. So we've got, and I'm also actually going to plug 5 into f because they gave me that value. So for f of 5, we can write 1/2. Again, they told us that. For f prime of 5, we're going to apply this formula here. So plugging 1 in for all the n values, I've got negative 1 to the 1. So that's just going to be a negative 1 out in front, or just a negative. We have n factorial, which is just 1, so that doesn't really change anything. This x minus 5 is going to end up in the numerator. And down below, I have a 2 to the 1 times a 1 plus 2, which I'll simplify later on. Next, I have f double prime and the rest of this. So plugging 2 in for n in my derivative formula. Negative 1 to the 2 just becomes positive 1. So this is going to be a plus we're writing for that term. We've got a 2 factorial upstairs along with an x minus 5 squared. Downstairs we have a 2 to the 2, a 2 plus 2, and don't forget this 2 factorial that was there as just part of the general Taylor formula. Finally, we've got 3 being plugged in for n in the derivative. So negative 1 to the third is just a negative. We have a 3 factorial. We have an x minus 5 cubed. Downstairs we have a 2 to the third, a 3 plus 2, and we have a 3 factorial. You could leave it like this, no need to simplify. But if we did want to simplify, we could write 1/2 minus, this is going to be x minus 5 over 6. So 1/6 x minus 5. And here, this next term, the 2 factorials cancel. Left downstairs we have a 4 times a 4, which is going to be a 16. So we have 1/16 x minus 5 squared. And finally, this last term will be negative. 3 factorials cancel. We have 2 to the third, which is 8 times 5, so that's 40. So minus 1/40 x minus 5 quantity cubed. For this part of the problem, they want the radius of convergence of the Taylor series for f about x equals 5. So before I can figure out radius of convergence, I need to know a little bit about the nth term. And while I'm figuring out the nth term, I might as well just write a formula for the Taylor series of f in general. So I'm going to write f of x equals summation from n equals 0 to infinity of, and now in general we have the nth derivative times x minus 5 to the n over n factorial. So I'm going to write my nth derivative here, just this big thing, all of that, no changes, times, now we have, let's see, it was x minus 5 to the n over, it would be n factorial. There we go. So this is my nth term right here. Now, this is not quite a geometric series. Even if you cancel out these n factorials, which I'm certainly going to do, so this is really negative 1 to the n, x minus 5 to the n over 2 to the n, n plus 2, all of this stuff. Even with those factorials canceled out, this still is not a geometric series because you have just this n plus 2, which is not exponential. So we're going to have to use the ratio test on this one. So I'm going to have the limit as n approaches infinity of absolute value of, and now I need the n plus 1th version of this. But because I have absolute value, I can at least get rid of this negative 1 to the n. So I'm going to have x minus 5 to the n plus 1 over 2 to the n plus 1, and this will just be n plus 3. So I'm going to have all of that over the nth term here. So just all of this stuff without the plus 1s, like so. And now let me do a little fraction math. Same change flip. In the numerator, we've got x minus 5 to the n plus 1 times 2 to the n, n plus 2. And then we also have in the denominator 2 to the n plus 1, n plus 3, and x minus 5 to the n. Cleaning things up, reducing a little bit, these 2's can cancel, leaving me with just a 2 downstairs, subtracting with my exponent rules. And these x minus 5's can partially cancel, leaving me with just an x minus 5 to the first power upstairs. So when the dust settles upstairs, I've still got an n plus 2 and an x minus 5. I still have that limit as n approaches infinity as well. And downstairs, I've now got a 2 and an n plus 3. As n approaches infinity, I can ignore this plus 2 next to the n and also this plus 3. So I essentially have n times x minus 5, and I also have an n times 2. N's are going to cancel. We're left with just absolute value of x minus 5 over 2. And now for my radius of convergence, for the series to converge, this stuff has to be less than 1. To get the radius of convergence, I just make sure that my x has a coefficient of 1. So to do that, I have to multiply everything by this 2. And I have absolute value x minus 5 less than 2. Because I have this in x minus a less than whatever form, the whatever over here is going to be my radius of convergence, so my ROC then is 2. For the last part of this problem, they want us to show that the 6th degree Taylor polynomial for f about x equals 5 approximates f of 6 with error less than 1 over 1,000. So here again was my f of x that I wrote in part B. So this is giving me the whole series for this Taylor polynomial about x equals 5. Now, if I'm trying to approximate f of 6 with a 6th degree version of this, basically I'm plugging 6 in for x, and then I would be writing only the first, I guess, 7 terms, because the degree is the exponent, so the first 7 terms of this, and just kind of stopping there. So let me start by just plugging 6 in for x, so we at least have a better picture of what my series is going to look like. So that would be a negative 1 to the n, and this would be, let's see, 6 minus 5 to the n is just 1 to the n, which is just 1. So we really just end up with negative 1 to the n over 2 to the n, n plus 2. This is f of 6. And again, if I'm approximating this with a 6th degree Taylor polynomial, that means I'm just writing out all the terms up to n equals 6, adding those together, and whatever we get, we get. Now, if I want to figure out the error on this, the key here is recognizing that we have an alternating series. This series alternates, and more than that, since it's bottom heavy here, we're decreasing an absolute value to 0. Because the terms alternate and decrease in absolute value to 0, we know that the error is going to be less than the absolute value of the next term. That's the alternating series error bound. So we just need to figure out what the next term is. Well, if we're doing a 6th degree Taylor approximation, that means the next term is going to be n equals 7 plugged in all this. So that's going to be, this negative 1 goes away with the absolute value, so we're just going to have 1 over 2 to the 7th times 7 plus 2. So that's our error, is going to be less than that. 2 to the 7th is going to be 128. 7 plus 2 is 9. And we essentially need to show that this is less than 1 over 1,000, which it looks like it's going to be. But it would be easier to prove this if we can just multiply this out. So we have, I'm just going to split this up. So we have 9 times 100 is 900. 9 times 20 is 180. So we have, let's see, 900 plus 180 is 1,080, plus another 72 because of 9 times 8. So that's going to be 1,152, 1080 plus 72. Yep. Since this is a larger denominator than 1,000, that means that this fraction is smaller than 1 over 1,000, and this proves what we set out to prove at the beginning of this problem.